All right, this is DiffeHellman key exchange, okay? It's the second to last lecture for this class, okay? Now, we talked about AES and DES and all those. Those are symmetric key encryption systems. Symmetric is same key. So if me and Carol were trying to encrypt something, I would have to get her the key somehow. And how do you do that across the internet? Well, DiffeHellman key exchange allows you to transfer a key over an unsecured network, okay? Which is kind of cool. It's actually very simple the way it works, and they go into it extensively inside the crypto book if you're reading that. It's really pretty good. Okay? All right, here's how it works. Alice and Bob, it's usually Alice and Bob, and Eve is the eavesdropper. Alice and Bob, they share a DiffeHellman group, GP. Okay? A large prime number P and an integer G. That's what they're sharing. Okay? So me and Carol would share those. Okay? Alice normally chooses G and P and shares it with Bob. It really doesn't matter, but one way or another, they both have to come up with the numbers. So we would share the G and the P. Okay? Then Alice generates a large random number X. Okay? So Alice generates this large random number, doesn't send it to Bob, but Alice sends the half key, which is G to the X. Okay? Mod P. So what we do is generate a large random number X, then do G to the X. Remember, we both know G and P. So if I do G to the X mod P and send those results across, would Carol know the original X? No, she wouldn't. But she can work out the result. Okay? So, generates a large random number X and sends the half key, large X, which is equal to G to the X mod P. So real simple math so far. Okay? It's normally a very large number, but obviously for our case, they're going to be very small numbers, so we can do the math. Okay? Then Bob generates a large random number Y, and also sends the half key, Y, which is G to the Y mod P. Okay. Remember, we both have the same G's. We shared those already. We're not sharing the large random numbers. What we're doing is we're sharing the results of the formula G to the Y mod P and G to the X mod P. Okay? So we're sharing the half keys. So far, so good. Okay? Okay, then we compute the keys. Okay? Alice receives Bob's Y. Because remember over here, Bob sent the Y. See at the bottom here, Bob sent Y. So now Alice takes the Y she got from Bob and calculates Bob to her X, mod P, for her key. Then we take the small y. So Bob takes the Y he got, he calculated with the X he received from Alice. So X to the Y mod P is his key, and they're the same. We're going to see in math how it works. But it's very, that's it. We're done. That's the entire thing. It's very simple. Okay? Now, advantages. It says key K is at least as strong as the strongest half key. Okay? Neither Alice nor Bob can completely sabotage the resulting key. We can't see what the other person has because I never gave you that initial large X or large Y random number. Okay? Disadvantages. I don't have a clue who I'm setting this to. So if someone intercepts the communications, if Bobby intercepts Carol's communications, now I'm really talking with Bobby instead of Carol. So there's no authentication, no prevention of replay or flooding, and does not prevent against denial of service as well. But it is a way to transport the keys. So let's look at an example. Okay. So consider the DiffeHellman key exchange sequence or scheme where G is 3 and P is 353. Remember, those are the two we passed, the G and the P. Then Alice and Bob pick X of 97 and Y of 233. Complete the half keys and then the key. Okay? That's the exact way the assignments are written. Right? Now, let's look how it works. So, the answer is, okay, so remember we shared G and P, the 3 and the 353. Those are the G and the P. Okay? And we chose 97 and 233 as our random numbers. So if we took the 3 to the 97 mod 353, we get 40. and we take the 3 to the 233, mod P, we get 248. Those are our half keys. Okay? Now, here, we take the 40. Remember, the 40 is the result of the half key. 40 raised to the 233, mod P gives us 160. And then Y, or whatever, the 248 raised to 97, mod P, and get 160, so they're the same. Very, very simple math. This is the entire math right here. Okay? Think of this as two different people. Because you're seeing both sides of it. But in the real world, you wouldn't. You would only see one side of it. Okay? Like up here, I would know the G and the P. I would pick my X, but would not share it. Okay? I would pick small x, would not share it. Okay? Then I would share the result of 40. Okay? Then the person on the other end would use that 40. Remember, I calculated the 40. They would use that 40 along with the y that they chose and end up with the same key that I got. Okay? It's really, really simple math. Okay? This is probably the easiest math of them all. Okay? Understand what I just said? See how that works? It's very. And I'm going to give you questions exactly like this for the homework. There's 10 of them. What I want you to do is like this. I want to know the half keys and then the key. Okay? Now, in theory, the key should be the same, but do the calculations anyway to be safe. Okay? All right. Now, it's another example. All right. So, consider the DiffeHellman scheme where G is 2 and P is 11. Again, we share the G and the P. Alice and Bob pick X of 6 and Y of 8. Compute the half keys again, and then the key. Remember, we shared G and P. We shared the G, the 2 and the 11. That's what we shared at the top here. We shared the 2 and the 11. So Alice picks an X of 6. 2 to the 6 mod 11 is 9. So Alice sends the big X to Bob. Okay? Bob has picked 8. So Bob takes the G and the P and calculates G to the small y mod x and gets 3. Bob sends the 3 to Alice. Okay? So far so good? So Alice down here, remember, Alice had the x, the 6, never shared it with Bob. Okay? But Alice received the 3 from Bob. So on the bottom of the key, the 3 raised to her x, which was 6. 3 to the 6 mod p is 3. And Bob, on the other hand, kept his y secret, and his y was 8. He received the 9 from Alice. So 9 raised to his 8 mod 11 is 3. So our key is 3. Everybody see that? It's very, very basic math. And that's all there is to it, right there. I mean, that one slide is the entire thing. Well, other than the numbers to start with. It seems too easy to be true, but it is. It works perfectly. It's still used today. Okay. Still used today. Now, obviously, we normally be working with 140-bit numbers, but it's easy enough to see here that it actually does work. Okay. Now, I'm going to continue recording for a second. I'm going to show you what the assignments are. Okay. Now, I'm going to up the one with the answers, the one without the answers. Okay.
Still recording, so
Basically, it says, go to D2L quizzes section to do this. Okay. Now, I'll show you what the questions are, just so you have an idea. The questions are just like this. But I put them into the quizzes section. You know, I give you, consider the DiffeHellman keys exchange with GP, X and Y, just like the 2 examples. You do 10 of these and put in the results.
The only answers you want is
Actually, let me bring up D2L so you can see it. All right, D2L. Oh, I didn't like that one. They like that one. All right, let's go to DiffeHellman. Do the 24th. You'll notice it's the same day as your AES is due. Start quiz. No time limit. It's set at 2 hours, but I'm not enforcing the time limit, so you can open it and work on it, whatever you want. Okay? Come on. You can do it. Here it is. For each one, I give you the value. And I says, complete the half key for each, then complete the key for each. And that's it. Now, someone always screws this up. All I want is the answer in the box. Do not put x equals 3. All I want is 3. So I'm telling you, complete the half key x. Just put 3, or whatever it is. Okay? If you put in 3, it'll grade it correctly. If you put in x equals 3, it'll mark it wrong. They'll have to go back and check it.
He'll have to do it manually, so do that.
Oh, half the class will, I guarantee you.
So the keys are always the same. So
They should be. If they're not, then there's probably something wrong with your math. But I have had people in the past, compute the first key and use that as their answer. Well, they screwed up. So there was an error in their math. And if they had calculated both, they would have saw, whoa, I screwed up in my math. They don't match. Then they could have figured out what the error was. See what I mean? That's why I got to do both to make sure they match. Okay? You get 10 of these. And then you're done. It's not difficult, but you will see the exact sort of thing on the test. Okay. So know how to do it. It's nothing difficult. Okay? Everybody okay with that? I said it's very simple. It's probably one of the easiest algorithms. Dr. Schnoy didn't even cover it at University of Tulsa. He's like, that's too easy. I said, yeah, but it's kind of cool to know that you can do something like
yeah,
this.
that'd be nice.
Yes. So, all right, let me stop the recording here.